Um, all right, Bismillah, Assalamu alaikum. Um, so let's get started with new chapter. So inshallah we'll start chapter 8, which deals with lipids and membrane and membrane proteins. So before we start in this chapter, uh, remember at the beginning of the class we said, if you crack open a cell, you'll find four kinds of macromolecules, and we talked about you'll find proteins, which are polyamino acids, polypeptides. You'll find nucleic acids like DNA and RNA, which are polynucleotides. You'll find carbohydrates or polysaccharides as polymers of carbohydrates, and then you'll find lipid membranes and lipids, right? So this our whole semester is going to be these four classes of biomolecules. And we've talked about proteins a lot. We talked about a lot about proteins and enzymes, all those things. Now, so proteins gone. Now we'll start with lipids as a second class of biopolymers. So that's where we're headed. Now, um, if you recall, we said lipids are essentially hydrophobic compounds, and we know this. So let me just Okay, so we said lipids are essentially nonpolar or hydrophobic compounds. In fact, they're not only nonpolar, and you'll find that lipids actually are more accurately described as amphipathic molecules. So amphipathic molecules are molecules that have both a nonpolar end and a polar end. So they have both hydrophobic and hydrophilic, both, right? So lipids are basically defined as compounds which are very soluble in organic solvents, but specifically lipids are amphipathic molecules. And lipids have many important functions. They are important as a source of energy, as you know, fats are source of energy. Uh, they are source of energy storage. They're important in cell membranes. They are also served as building blocks of hormones, and we'll talk about this a little bit later. And then, as well as serving as a precursor for vitamins, and they also serve as insulation and protection. And and you see this um, with Arctic polar bears, for example, and things like other animals that have a lot of fat around their bodies. But the point to take home is lipids are amphipathic molecules. They have both a polar end and a non-polar tail. And the example of a lipid would be something like uh, we'll talk about this, what's called fatty acid. And fatty acids are basically things that have, you have CH3, for example, and CH2, 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 many times, right? And at the end you have a carboxylate group, right? So this part is our polar part, and all of this would be the non-polar tail, and that's example of an amphipathic molecule. Okay, so moving on. So lipids is a huge class of organic compounds, and fatty acids is one branch of them. Steroids is another branch of them. Triglycerols is another one. Phospholipids or glycerophospholipids are another one. Um, and the one that I'm highlighting in purple or circle in red, these are the ones we'll talk about. There's four classes of lipids, but we should know that lipids are a much bigger class of molecules. Um, Waxes like honey wax and beeswax, as well as sphingolipids are other examples. We'll talk a little bit about them as well. Okay, so we'll go and talk about each one of them. We'll start talking about fatty acids, then we'll talk about triglycerol, we'll talk about phospholipids. We'll touch a little bit on these two guys as well, and towards the end of the class, we'll talk about on steroids. Okay, so if you again, the same slide is shown here. Um, so let's talk about fatty acids. What are fatty acids? And as the name suggests, fatty acids are carboxylic acids, right? So fatty acids are carboxylic carboxylic acids. So here's an example of a fatty acid where you have a carboxylic acid group, right? And these are basically a hydrocarbon long chain hydrocarbons that have carboxylate group at the end. They have a long chain of hydrocarbons, right? So acetic acid, if you remember, acetic acid is CH3 C double bond OH. That's acetic acid. But if you just make this group longer, that's what fatty acids are. They can be different number of carbons shown on the left hand side on this example here. This is a C12 fatty acid. It has 12 carbons, 1 2 3 4 5 6 7 8 9 10 11 12, right? And it has a name and we call it laurate and so on and so forth. This is a saturated fatty acid, and we'll talk about this a little bit in the next slide as well. Saturated fatty acids are fatty acids that do not have any double bonds. It contains no double bonds. You see, you have all single bonds, single bonds here. There's no double bond in the chain. Of course, this double bond is not counted because this is part of the carboxylate acid. So they have no double bonds in the fatty acid chain, in the alkyl group chain. Okay. Um, so we said fatty acids, they have different number of carbons. So you can have, they have different number of carbons. Oops. Can I erase this? Let's see if I can erase this. Yeah. Okay. They have different number of carbons. Let's erase that again. Let's try that again. Sorry. So they have different number of carbons, right? 12, 14, 16, 18, 20, and they have different names. What I want you guys to know, the length of the fatty acid plays a role in the chemical character of the fatty acids, and we'll talk about this in a few minutes. But there's usually even number of carbons, right? So you have 12, 14, 16, 18, 20, 22, 24. But sometimes you can also have odd number, but normally, typically, usually they are even. They can contain odd numbers as well. And if they have a CC double bond, we call them unsaturated. If you have only CC single bond, we call them saturated. So here, if you look at these ones, these are all examples of saturated ones because they don't have any single any double bonds. And one of the point to note is as the number of carbon increases, as you go from 12 to 14, right? As you increase the number of carbons, the boiling point, the melting point, sorry, also increases, right? And this has to do with the fact that, okay, so as we were saying, fatty acids can be saturated or they can be unsaturated, and primarily, again, we said saturated and unsaturated depends on the presence. So the saturated or the unsaturated, they really depends on the presence or absence of these double bonds, right? So there's no double bonds here. This would be a saturated fatty acid. You have a double bond here. This is called unsaturated fatty acid, right? And actually, the double bond that we have, and we'll see this, the double bond we have in fatty acids are in fact only cis double bonds, and cis double bond causes a kink in the structure. So this is an important point to understand. So the double bond, you have a cis which causes a kink and kink, really what that means is a kink really means a bend. So you have chain going like this, it bends like that. You chain like this, bends like that. And if you don't have a double bond, if you have just single bonds, then the chains are pretty much straight, right? So it basically goes like that and is a straight. Otherwise, you have a kink in unsaturated fatty acids. Okay, and that's shown here as well. So you can look at this guy here. Based on this, you'll say this is saturated. This is straight line. This is saturated. This is saturated. So all of them are saturated fatty acids because they have no kinks in them. They have no bend in them. Whenever you have bends, you'll say these are unsaturated fatty acids. So just by looking at them, you can figure out whether you have saturated or unsaturated fatty acids, right? And it turns out, the absence of these double bonds, they actually have a very important physical uh, implication on the properties of these fatty acids. So we said saturated fatty acids have only CC single bonds, right? And as such, they are pretty straight, right? And then the other ones are pretty straight, and then the other ones are pretty straight, and so on and so forth. The fact that they are pretty straight, they can really like line up very nicely with each other, and they can pack very nicely. So they can they can fit closely together and pack, and as a result, these they have a lot of this strong hydrophobic interaction with the tails uh, touching each other. So they have strong hydrophobic interaction, and as a result, they have a higher melting point. You need to give a lot of heat to break up these interactions, right? And that's why they are usually solid at room temperatures. Right? Um, Unsaturated ones, as we said, right? If you have an unsaturated one, um, they have one or more double bonds, and we say the double bonds are cis. Please note that, right? This is cis. The hydrogens are both on the same side, and that cis causes a kink in the chain, right? This is a cis as well. So you have chain kink, and you have a kink, right? And as a result, these kinks do not allow them to pack very nicely, and they have fewer interactions between them. They're not as nicely packed, they're more like loosely packed, and they can be broken away very easily by a little bit of heat. So they have low melting points, and they are liquid at room temperatures, right? And again, same thing is shown here. The nature of double bond causes a kink, cause a disorder, and it makes them very fluid, very liquidy. So you have a saturated fatty acid, and then you have unsaturated, and if you have more, as you have more and more double bonds, you have more and more kinks and less packing, which causes less melting point. Okay. And that's shown here as well. So for example, if you have a saturated fatty acid here, and this is a C18 fatty acid, 18 carbons, right? And then the name is called stearate, and we'll see this later on in the next couple of slides. So it can pack with each other very tightly, so it's solid at room temperature, and you need to heat it up to 70 degrees before it starts melting. But if you have one double bond, right, and this is called oleate, right, it has a bit of a kink, and the melting point is from 70, it comes down to 13. It's liquid at room temperature. Room temperature is 25, so it's liquid at room temperature. Linoleate has two saturated double bonds, one here and one here. So it's even less tightly packed than oleate, than this guy, and as a result, it is so unstable that you have to cool it down to minus 17 before it starts to become solid, right? So these two are both very liquid, and these differences are shown to be due to the cis double bond and the kinks the structures have, and they cannot pack properly. Okay, so what I want you guys to know, you can have saturated fatty acids, right? 10 carbon, 12, 14, 16, 18, 20, and I've talked about 22, 24, 26, but mostly it's from C12 to C20. These are the fatty acids. I want you to know one of them, just memorize one of them, any one. Um, so I'll just write this, explain this properly. So so if you want to memorize, for example, palmitate, this is a C16 fatty acid, and you should know the structure, which is basically 16 carbons. And then don't worry about this, no need for memorizing melting points. So you should memorize the common name, you should memorize the C16 colon 0. That means 0 means it has no saturated, it has no double bonds, and there should be 16 carbons in the chain, in the full molecule completely, right? So you should know one example of a saturated fatty acid and one of an unsaturated fatty acid, right? Again, fatty acids, unsaturated ones, you can have C16, 18, 20, but if you look closely, what you find that they actually have, let me just do that. They actually have, C16, right? So we can actually write C16 colon 1, colon 1 means one double bond, and then you put delta 9. It means at 9 carbon you have a double bond, right? This is called palmitoleate, that's the name, or you can say oleic acid. Oleate would be C18. It has one double bond. Linoleic would be C18 that has two at carbons number 9 and number 12. So you have to make sure you understand that. You can have 3 double bonds or 4 double bonds. So just memorize one from here, the chemical formula, the abbreviation as well as the chemical formula, right? Don't worry about these. So if I say draw the structure of a saturated fatty acid, you'll say, oh, it is C16, and the name would be, palmitate, or palmitic, anything you can write. And you can say, well, it's C16, so I have CH3, I have CH2 many times, and at the end I have COOH. So this CH2 has to be, so you have 1 and 2 and 3, and this has to be 13, right? So that's the structure of palmitic acid. And you can do the same thing for the unsaturated ones. If somebody's not sure about this, please ask me in the class. I'll be happy to write this and explain this, right? So again, saturated ones are solid at room temperature because they pack very tightly. The unsaturated ones, they have a kink and they are liquid at room temperature, right? And the example would be olive oil has a lot of unsaturated fats, unsaturated oil, and butter has a lot of saturated, um, a lot of saturated fatty acids, right? And that's why, for example, if I say coconut oil, we know coconut oil freezes at room temperature, becomes solid at room temperature, and therefore you would think coconut oil has a lot of saturated fatty acids, saturated fats. Okay. The second class of lipids we'll talk about are what are called triglycerides, triacylglycerol. So triacylglycerol, they're also called triglycerides as short. Sometimes you hear that word triglycerides, or triacylglycerol. And triacylglycerols are basically esters. These are esters. If you remember the functional group esters, which is this part, they're esters of glycerol with fatty acids. Now, glycerol, you should all know what glycerol is. Glycerol is a 3-carbon alcohol that has OH, OH, and OH, and carbon must have 4 bonds, so you have 2 here and 1 here and 2 here as well. Okay, and these OH on these sides, they can react with carboxylic acid groups, right? So they react together to give you an ester linkage. So a triacylglycerol, it has 3 acyls shown in red part. These are called acyl groups. So you have 3 acyl groups linked with glycerol, and that's why they call triacylglycerol. And these are actually same thing as what's called fat. If I say what is fat, if you go shopping and you see meat that has white stuff on it, that's the fat. And fats really are triacylglycerols, or they are triglycerides, which is basically glycerol that has 3 fatty acids attached to 3 OH, right? That's called triacylglycerol. So this is triacylglycerol, for example, again, right? So you can see the glycerol part shown here. Let me just highlight this. This is glycerol part, right? And you have, let's do that. Let's put right. Okay, and then you have got these 3 fatty acids here. 1 fatty acid, 2nd fatty acid, and 3rd fatty acid, right? So this is fat or triacylglycerol. Okay, uh, it turns out in the old days you could take fat and you boil it with sodium hydroxide, some strong base, and when you boil it, sodium hydroxide actually, um, these actually can react. So make it red. Sorry, can break down these bonds, right? And when you break this, water goes in, basically it's a hydrolysis reaction. Water goes in, it breaks down the bonds, and you get back your glycerol, plus you get the fatty acids. But you don't just get the fatty acids, you get the sodium salt of a fatty acid, right? So this is a sodium salt of fatty acids, right? And that is basically what a crude soap is. I mean, a soap is nothing more than fatty acid that is saponified, or that has sodium salt of a fatty acid, sodium palmitate, sodium stearate, sodium oleate, and so on and so forth. So this was an interesting tidbit I wanted to show you guys about how fats can be used, and that's how they were made in the old days. You can make fats out of coconut oil, you can make fats out of olive oil, you can make soap out of olive oil, soap out of coconut oil, and so on and so forth. All you have to do is take some fat and you just boil with sodium hydroxide, and you get this solid material, which is the sodium salt of a fatty acid. So that's just for your information. Okay. So we've talked about fatty acids. We've talked about um, triglycerol. The third lipid we'll talk about are phospholipids, right? So phospholipids, they're also called glycerol phospholipid, and as the name glycerol suggests, they have glycerol in them again. So glycerol is this part here. This is glycerol, right? They have glycerol, and just like triglycerol, they actually have two acyl groups, right? So you have this fatty acid here and second fatty acid here, right? But the third OH where the fatty acid is, there is no fatty acid. So in phospholipids, what you have a phosphate group added here, right? So phospholipids look like triglycerols, but they have phosphate, and then they have something attached to the phosphate, which could be a hydrogen, or it could be more complex things. So if you have hydrogen, this is called, if you just leave it like that, just a phosphate by itself with hydrogen or without a hydrogen, it's called phosphatidate. That's the name of a phospholipid that has a glycerol part, two fatty acids, and a phosphate. That's it, right? Now remember, I keep saying at the beginning of the lecture, I was saying fatty acids or lipids are amphipathic molecules, that they have both hydrophobic and hydrophilic. So here you'll find that this is very hydrophilic, right? A polar, right? So this is polar, right? And this part is a very hydrophobic part. That's a hydrophobic part, right? And that's what fatty acids are. They also have hydrophobic, hydrophilic. That's how triglycerols are, or fats are. Fats have hydrophobic stuff and polar end. And phospholipids have very polar end, and also they have a hydrophobic tail. Okay, so again, there are different kinds of phospholipids you can have. Um, the first one we just talked about is called phosphatidate, and phosphatidate is the simplest one, where you have basically at the end you have just the hydrogen attached to the phosphate group. But you can have other things attached to the phosphate group as well, right? And depending on what, you can have amino acid serine attached to the phosphate group, and we call it phosphatidylserine. You can have something called ethanol amine, then we call it phosphatidylethanol You can have glycerol attached to it at the end again, and we call it phosphatidylglycerol, right? So again, I want you guys to memorize just one example of phosphatidate and any one of these guys, another one from these guys. Just two examples of a phospholipid. One would be the phosphatidate, the simplest one, and then one a bit more complex one. Okay, so again, this is phosphatidate. We said you have glycerol part here, you have one fatty acid here, you have second fatty acid here, and then you have a phosphate with an hydrogen or even nothing, and that's called phosphatidate. But if you have other things attached here, like serine, for example, then we call it phosphatidylserine, or something else could be attached here, and we'll see this in the next slide, right? So you have, so here's an example. So you have glycerol, so 3 carbon, right? One has a fatty acid, second part fatty acid, third part O, you have a phosphate. So this is phosphatidate so far, but then you add serine to it, and because it's serine, we call it phosphatidylserine. Or you can have something called inositol added to it, then we call it phosphatidylinositol, and you can have more complex ones as well. So just memorize the simplest one. I would say memorize this one because you already know serine, and you can just memorize that as well. Okay, So moving on very quickly, we said there are other types of lipids as well. Waxes are another examples of lipids, and waxes are really esters of long chain carboxylic acid and alcohols. So you have this um, this ester group here, right? On one end you have a you have the alcohol part coming here, and then this is the carboxylic acid part here. So you have a carboxylic acid and alcohol. So this part is from the alcohol, and that's from the carboxylic acid part, right? Or you can have another example of an ester with two aliphatic chains on both ends. These are waxes. I don't want you to memorize the structure, but I want you to know what they are. So these are esters of alcohol and a long chain carboxylic acid, right? So basically you can say the general structure would be C double bond O O and R1 and R2, right? And these would be examples of waxes. Okay, that's all. That should be enough. Okay. Um, There are other classes of lipids. I don't want you to memorize them at all. We don't have much time this semester. Things called sphingolipids. Sphingolipids are involved in cell signaling and apoptosis. These are very important events in cells. But that's all I want you to know, and don't worry about this, right? So that's all I want you to know. Sphingolipids are important lipids in cells, and they're involved in cell signaling as well as apoptosis processes, signal transduction, right? But don't worry about the structures at all. I don't want you to memorize that. Okay. Yet another class of lipids are called glycolipids. Glycolipids are extremely important class of lipids, and they're mostly important for cell recognition. So these glycolipids are on the surface of cells. So you have a cell, and then on the surface you have this something sticking out, right? And these these guys that are sticking out, these are glycolipids, and they're involved in cell recognition. And of course the biggest so I don't want you to know, just read this part, but don't memorize the structures, right? um, the glyco means of course glucose attached to the lipids, so you have carbohydrate things attached to lipids. um, but don't worry about memorizing structures. And the example that we know, this is another one. Nothing, we're not going to talk about this. I, the clear example of glycolipids are this ABO blood typing antigens, right? We know that you have this red blood cell. So this is a red blood cell. Red blood cell. On the surface of red blood cell, you have these guys sticking out, and these serve as antigens, right? So they serve as antigens. So they serve as antigens for um, uh, antibodies. So O antigen, for example, it looks like this. This is what O antigen looks like. A antigen, please note, A antigen looks exactly same as O antigen. There's no difference except for one carbohydrate moiety, one sugar residue, which is N-acetylglucosamine, like this guy here. So I don't want you to memorize it. All I want you to know that there is just one thing which is different between O and A. Same thing with B antigen. B antigen looks very much like O antigen, yet you have galactose here, whereas you have N-acetylgalactose, different one. So this is what causes AB blood typing. Um, so O, something is missing here. There's nothing here is missing here. A type has um, a a um, A antigen has this part here, which is basically this thing. B has something different. So we'll just do that. B has something very different, which is this, and AB has both A and B together, right? And that's what things are. Okay. Uh, Lastly, the last class of lipids we'll talk about are called steroids. So steroids are a class of lipids which are very different than what you've seen so far. They are composed of four fused rings called A, B, C, and D. So you have four rings. They basically look like this. six-membered ring called A, another six-membered ring called B, B, and then third one is here, six-membered ring called C, and the last one is a five-membered ring called D. Five-membered ring called D, and that's what steroids look like. And cholesterol is a member of steroids. Estradiol is a female sex hormone. Testosterone is a male sex hormone, and they're all derived from the same core structure. So I want you to memorize just one example, any one of them. So either progesterone or estradiol or testosterone or cholesterol, just memorize one, only one, for any one of them. And know that these are almost planar. They look like, if you look at, they almost look flat. And they're also amphipathic. That's the same thing we keep talking about, that all lipids are really amphipathic. So they have, for example, this would be, all of them would be hydrophobic part, and then they have this hydrophilic polar end, and polar end and polar end, right? And that's the example of, like here, same thing, all of this would be hydrophobic, then you have a polar end, and these are amphipathic molecules. And of course, a lot of cholesterol is very important, and a lot of hormones are derived from them. And an important point to note here is that cholesterol is an important constituent of membranes, and we'll talk about membranes in the next lecture. And we find that cholesterol is an integral part, a very important part of membranes. This is what cholesterol looks like. Again, I just want to highlight the polar end and the non-polar part, right? So this is the polar part of the molecule here, and this is the non-polar end, and that's why it's also called an amphipathic molecule. It looks sort of planar, right? Straight. It's not. That's the whole. Okay, so this is the end of this set of slides, and we'll stop here. And inshallah, I'll see if you have any questions. We'll take it in the class tomorrow, and then we'll talk about what is next for us. All right, take care. Assalamu alaikum.